Hi, welcome back. Hello. Hello.
Welcome to Ms. Carranza's 40 class.
Yes, welcome 4A. Good to have you back. As you can see from our It's Learning board here, we are going to be looking at two sections today. We're doing similar triangles, which will feel a lot like the similar polygons from last time. And we're going to do some parallel lines and proportional parts. In this, we're going to recover and remember some information we did in previous semesters when we were talking about parallel lines and those things transversals. Let's go ahead and jump right on into the action with some similar triangles. All right, let's identify what these are first. So to identify similar triangles, our first little weapon here is the postulate 7.1, the angle similarity. This says that if I have two angles in one triangle congruent to two angles in some other triangle, then the triangles are going to be similar. Let's get some triangles going here. If you've got your handwritten or your printed out notes, go ahead and fill this in. I've just got some triangles here. There we go. I've even named them. And it says two angles in one triangle congruent to two angles in another. So I'm going to put some congruent markings on two of those angles. There we go. And I'm going to put some congruent markings on two other angles on the other triangle. There we are. This information is enough for us to say that the triangles are similar to each other. We can't say they're congruent to each other because just off the angles alone, we can't state whether these sides are the same measure. And the only way they can be congruent is if all those side lengths are the same measure. We don't have that. We only know that the angles are congruent. So the best thing that we can say is that they're similar. Let's write our similarity statement for these two triangles. I'm going to write the name of the first triangle. That's the one on the left. And I get to write these letters in any order I want, and I can spell anything I want. I'm going to name it triangle ABC. I'm going to use the symbol for similar. Remember, it's that little tilde squiggle thing. And now I have to be careful about the order of the letters. I have to make sure that the corresponding points, those corresponding corners, are in the same order. I wrote A first. A has one arc for congruence. So as I look at the triangle on the right-hand side, I'm looking for the angle that has one congruent marking. That's this angle here at E. So I'm going to write the letter E first. The next letter that I wrote was B. That angle doesn't have any congruent markings. So on the other triangle, I'm going to look for the angle without congruent markings. That's F, which means my final letter in this triangle name is D. All right, so let's see how that's going to look like on your skill practice. I'm going to flip over so we can see that really quickly. Determine whether the pair of triangles are similar. Here we go. So questions 1 through 4 are going to be similar to this example we're about to do. All right, let's look at A. So with A, first off, I'm missing some letters in the name of this triangle. So can I have a letter from you guys that you want me to use for this other point here? Q. All right, so we'll use Q. All right, so as I'm looking at these two triangles, I notice right off the bat that the angle at L has the same measure as the angle at M. So I'm going to say those are congruent, and I'm going to say that they're corresponding. Now, as I look at the other corners, I have angle here at J48 and the angle here at P75. Those aren't the same measure. I can't say they're congruent. So I need to find out some more information, maybe about this angle here at K. If that angle measure at K is 75, then I can say that K is congruent to P and these angles become similar. Let's figure out the measure for angle K. If we recall back in chapter, I think 4, when we were talking about triangles, we looked at the triangle angle sum that said that if I add up all 3 angles in a triangle, I'm going to get 180 degrees. While I write this out, can you guys subtract 57 and 48 from 180 and tell me what you get? You got 75? All right, so now I know that the measure of angle K is 75. Oh, hey, that's the same angle measure as we got here for angle P. That means K and P are congruent. We're going to call them corresponding, and these two triangles are similar. All right, let's write the triangle similarity statement. I'm going to write the name of the triangle on the left first, and I'm not going to care what order I write the letters in. I'm just going to put them in whatever order I want. I'm going to write the similarity symbol. I'm going to write the triangle symbol for the next shape, and now I have to worry about the order. The letter L I highlighted blue, so I need the letter I highlighted in blue from the other triangle. That's M, so M comes first. The next letter was K, which is pink, so I need the pink letter from the second triangle, that's P, and then I have only one letter left. There's my similarity statement, and now I have to write the reason. My reason was from this postulate 7.1, the angle-angle similarity. And so my recommendation for you guys as you're doing your homeworks is to get that practice for writing out the postulate number and the name, so that way when you see this on a proof that you have to use it, you know what that postulate gets used for. Not too terrible, right? But it looks more complicated when I give you a figure without angle measures, like in B. So let's zoom in on example B here and take a better look at it, see if we can't figure this out. All right, I have two triangles. I have the triangle on the left, RSX, and the triangle on the right, STW, and I'm trying to figure out if they're similar. Well, the first thing I notice is that I have this line from R to W, and then I have this other line from X to T, and they intersect at the point S. If we recall way back early in the beginning of the year when we were talking about lines intersecting, we said that when lines intersect, they create vertical angles. Right here and right here are vertical angles. I think it was a little later, maybe chapter 2, we talked about vertical angles being congruent, and we had a theorem called the vertical angle theorem that said that if angles are vertical angles, like these are, R, S, and X, and W, S, and T, they're going to be congruent. So I can write that these two angles are congruent. And I'm going to give the reason. All right, by the vertical angle theorem. There we go. Note that I'm writing these reasons as I go, because I know from the directions I'm going to have to explain why I'm saying they're similar or why I'm going to say they're not similar, depending on what ends up being true. All right, so now I have these two angles congruent. Did you notice that I wrote the R first, RSX? I basically connected the R and the W, and I said that they were corresponding. It's because R and W end up on the same line. So they're like corresponding angles. Oops. Oops, I messed that up. Let me rewrite that, sorry. Trying to get rid of the pink only and I got rid of the right. Okay, so now I have these angles congruent with the black dots. Let's try to find some other congruent angles. If I can find even one other pair of congruent angles, I've got this solved. Well, I'm noticing right here, I've got some parallel lines. Chapter 3 taught us all about parallel lines, and in particular, it told us about parallel lines when they're cut by a transversal. I could pick either of these two lines, but I'm going to pick RW just because it seems to be the good line to pick today. Well, now that I've created this little setup right here, I noticed that right here at R and right here in W, I have alternate interior angles. And back in chapter 3, we had the alternate interior angle theorem that said when we have parallel lines cut by a transversal, these alternate interior angles are congruent. So that's going to be my reasoning. And I believe it was a theorem. Feel free to correct me in the comments if you flip back to that chapter and it's not a theorem, but I think it's a theorem. All right, I have two pairs of angles being congruent. That tells me these triangles are congruent. So I'm going to write my similarity statement. Here's my first triangle. We'll call it RSX. That's the triangle on the left. There's my symbol for is similar to. Now here in these angles, I said that R was corresponding to W. So since I wrote R first, I'm going to write W first. Then I'm going to write S corresponds to S, and T corresponds to X, so I'm going to write T. Now I have to give a reason why I said the triangles were similar. We're still using postulate 7.1, the angle-angle similarity postulate. Give me questions. We're feeling okay on this? That made sense? All right. I love the conversation. It definitely sounds on topic. Let's continue it a little later, okay? Cool, thanks. Also, to prove that triangles are similar, we have two theorems. And these are going to feel really similar to ones that we've already worked with. The first one is called the side-side-side similarity. And this says that when those corresponding side lengths of two triangles are proportional, the triangles will be similar. This feels a lot like the side-side-side congruence, where we just had to show that all three pairs of angles were congruent to each other. Now we have to show that they're in proportion. That means that I write fractions, two fractions equal to each other, where one pair of corresponding sides creates a fraction that's equal to some other pair of sides. If I can show that for all three sides, so it's not enough to do it with just two, I have to get a third angle going in there, and I have to get all three pairs of sides to have the same fraction, I'm allowed to say the triangles are similar. So this is a proof thing, a determine if they're similar setup. The other one that we have is the side angle side similarity. And this feels again a lot like that congruence that we had from chapter 4, I think it was, when I had two triangles sitting there and I wanted to show they were congruent. This one wants the lengths of two sides to be proportional. And notice we have this word and in there. That means we need to hit two different things happening. We need the sides proportional and we need the included angle congruent. All right, let's talk about what all that means real quick. The length of two sides being proportional, that's any two sides in our triangle. Being able to be written in such a way that the fractions we create with their measurements are equal to each other. So it's going to feel a lot like the one we just talked about, but you only have to do it with two sides. And then you want the included angle. The included angle is the angle that gets created by the two sides that we worked with. So these two angles here, and we want them congruent, the same measure. If we can show these two things, then we can say the triangles are similar. Let's use this information. Here on example 2, and I believe this is going to help you with your skill practice 4 through something. 4 through 9? Double check it. 4 through 8. Okay, this will help you skill practice 4 through 8. I'm going to do question number B. So we'll do B together. And then we'll do 2A together. Okay. So those are the ones we're going to do. All right, so let's look at B first. I'm noticing here that A is shared between both the small triangle here on top, AEF, and then the big triangle that it's sitting on top of, ACB, which means that by reflexive property, A is congruent to itself. So I'm going to jot that down real quick. A is congruent to itself. All right, so I have part of my setup. Now I need to show that the sides are in proportion. So I need to look at the side of this triangle from A to E, and I'm going to compare it to this side from A to C. And I'm going to look at that in terms of this other pair of sides from A to F and from A to B. And I want to look at the fractions that get created from both of those. So I want the fraction created by that corresponding side A to E and A to C. And I also want to look at the fraction created by the other pair of corresponding sides, A to F and A to B. Okay, A to E is 8. A to C is this much 8 plus 4 more, or 12. Okay, let's get that to simplest form. 8 and 12 are both divisible by 4. 8 divided by 4 is 2. 12 divided by 4 is 3. All right, we're going to do the same thing for this other fraction. And it's the exact same thought process going on right here. So I have 10 over 15. 10 and 15 are both divisible by 5. 10 divided by 5 is 2. 15 divided by 5 is 3. The fractions are the same. Those sides are proportional. And so this triangle, AEF, is similar to triangle ACB. AEF is similar to, running out of room, triangle ACB. And the reason, because this has an explain your reason, is by theorem. I think the number was 7.3, the side angle side similarity theorem. Questions? No questions, nods that it makes sense. Awesome. Let's look at 2A. With 2A, I have no angle measurements. I have no way to say that by the angle measures, any of the angles are congruent. Nor do I have any angles being shared like in B, and I don't have any vertical angles like in A. So I have to do this purely off of the 3 sides that I'm given, which means I'm likely going to be creating a setup with theorem 7.2, which was the side similarity theorem. This theorem said that I need to check to see if all of the sides are in proportion. That is, when I create a fraction out of the sides, that the number I get, the fraction I get at the very end, is equal for all 3 pairs of sides. Now, here's the hard part with this. Without knowing what angle measures there are, how do I know which corner corresponds to which corner? Well, what we're going to use is we're going to use the side lengths. The shortest side of one triangle is going to correspond to the shortest side of the other triangle. And I'm going to do that across all three of the triangles. The 12 is the medium side length on the one on the left, and 9 is the middle on the one on the right. And 16 is the biggest side here for this triangle, and 12 is the biggest side for this triangle. All right, I know which sides I'm looking at. Time for me to figure out what the fractions are and if things are similar. All right, I'm going to write the fraction on the left on top and the triangle information on the right on the bottom, for no other reason than that just seems to be a decent order. 8 and 6 both divisible by 2, so I get 4/3. Please double check to make sure that I'm simplifying these properly and then I'm doing this division properly, because I'm also watching to see if there's questions in chat, so I'm distracted. For this one, because I chose to write the left triangle on the top in this fraction, I have to make the same choice for all of my other fractions moving forward. When I first set it up, I'm free to write my fraction whichever way I want, but once I've made my choice, I'm stuck with it for the duration of my work for this particular problem. Dividing 16 and 12 by 4 gives me that. Okay, all three fractions are the same. That means that those side measurements are all proportional. And so, yes, theorem 7.2, the side similarity is what worked here. Questions? No questions, all seeming pretty easy, huh? Good. Good. Did have a question in the chat. Can we use ratios? Yes, that's definitely what these are. These are ratios. Awesome. Thank you for that question in the chat. Our next theorem is our properties of similarity. The good news is all of these are totally familiar. It's the reflexive property, the symmetric property, and the transitive property all over again. So as a reminder, here's what they say. The reflexive property says that a thing is similar to itself. The symmetric property says that if I'm writing a similarity statement, I can switch the order of my similarity statements and everything is still okay. The transitive property says that if I have one shape stated as similar to another shape, and that second shape similar to a third shape, then the first shape that we were talking about must be similar to the third shape that we were talking about. Watch out if I toss another proof at you, if we've got this kind of chain thing happening. Now, we noticed here that we had some similarity pieces happening. Did you notice? We can use that with some algebra, and really that's the only way I have of making this more difficult, is to throw some algebra at you. And if we look at our skill practice, I do that here on questions 5 through 8. All right, so let's jot down that this example will help you with questions 5 through 8. So you can either write it in your notes, example 4 helps you 5 through 8, or on your skill practice on questions 5 through 8, you can write down that example 4 in your notes is what's helping you. All right, I've been asked to find a side BE. There's BE. It has a variable of X for me. Nice, this makes it easy for me to work with. Hi, did you guys got a question? All right, just checking in. First off, before I can go anywhere, I need to see if these triangles are similar. They share an A, so A is going to be congruent to A. And since I have variables, I'm going to go ahead and assume that these triangles are indeed similar. That's what's going to make this work. Since they're similar, I have to look at corresponding sides. This side BE is going to correspond to this side CD. And so I can write a fraction that says that BE is in a ratio, in a fraction, whoops, with CD. Let's write this a different way. I want them to be in proportion. So I need two fractions that are equal. And here are my corresponding sides. Now I need to find two other sides that are corresponding in these two triangles to help me out. If I look at AE, it has a variable. And since I don't yet know what value this is supposed to take, if I choose this side, it's not going to be helpful. So I'm going to choose this other side, that one. And then I want this long one from A to C. All right. I'm going to write the small triangle information on the top. There's BE, and here's AB. And I'm going to write the big triangle information on the bottom. That's 3.5 and 5. And now this looks exactly like what we did last time in section 7.1 with that whole cross product thing. So make sure that you're writing out. I know for too many of you, it's super easy to just think this through. I'm going to multiply the numbers and then I'm going to divide, and you can stick it in your calculator and it's super easy. But please, 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 while this, hang on, my computer decided to freak out. There you go. Well, this is, it needed a brain break. There's too many fractions. While this is still easy, I want you please to write down that you have to do this cross multiplication thing. Okay, and then you can go through and use your calculator to help you with that multiplication. But please, please, please write down what it is you need to do. We're trying to make sure that you're feeling comfortable and ready for Algebra 2 and Pre-Cal and Calculus, where the fractions that look like this aren't simple numbers. They're crazy, weird, polynomial things with a bunch of X's and maybe some Y's and some other squiggly symbols. But the process is the same. Fraction equal fraction, cross multiply, and solve. Questions on how we do 5 through 8 on your skill practice? All right. Let's jump right into the next section because it's very much related. You're going to see this cross multiply thing come again. Let's take a look at 7.4. We're solving problems using proportions again, but we're going to do this on parallel lines. The very first theorem that we encounter in this new section looks actually almost identical to the problem we just finished doing. And in fact, it's related. But in the problem that we just finished doing, we took one small triangle and checked the ratio against the big other triangle. In this case, listen to what this theorem is saying. The triangle proportionality theorem. It says, if a line is parallel to one side of a triangle and that line intersects the two other sides of the triangle, then the line divides the sides into segments of proportional lengths. That means that this piece written in a fraction with this piece is going to be equal to a fraction of this piece and this piece. Okay, we're going to have two fractions. And in one fraction, we're going to have this section of the segment and this section of the segment in whichever order. Right now, I'm doing the left section and the right section, left on top, right on bottom. It doesn't matter what order you've picked it for the first fraction, but once you've picked the order, you have to use the same order in the second fraction. Otherwise, this thing breaks. Okay, let's use this idea to find the length of a side in here. All right, we're gonna get some color going. I've got in triangle PQR, segment ST parallel to segment RQ. So that thing parallel to that thing, we've got to set up just like this theorem. So PT, they've given me some information on, so I'm going to highlight that in a color. They've given me information on TQ, so I'm going to highlight that in a different color. They've given me information on SR, so I'm going to highlight that to make it easy to see. And then they want me to find PS, so I'm going to highlight that with my fourth color so that I can set up fractions and ratios that look like the example I have in my theorem. All right, let's set up that proportion, those two equal ratios. All right, on the left-hand side, I'm going to do the leftmost segment. I'm going to do the part on top to be on top and the part on bottom to be on the bottom. So PS on top, SR on the bottom. Now, because I made that choice for the segment on the right, I have to pick this piece that was on top, which is PT. That goes in the numerator. And TQ is going to go in my denominator. All right, now I just need to find the information that match my colors, and I'm going to throw that in there. Because I don't know what PS is, I'm going to give it a variable. X is the easiest variable to deal with. I was told that SR is 2.5 and PT, which I colored in pink, is 7.5. And then the blue segment I was told was 3. And once again, we have that exact same setup where we have two fractions equal to each other. I can cross multiply and solve. While I do this, go ahead and hit me up with questions in the chat or live, whatever you prefer. You can go ahead and get started on, whoopsie. Which part of homework 7.3 does this example look the most like? Hopping over to here. Looks like that is 3 through 5. So go ahead and start on number 3 while I finish out the algebra for this one. Alrighty, I found my answer. Circling it, checking for questions, looking at my chat, don't see anything yet. Looking around the room. Feeling okay? Easy enough? All right. Now the next theorem that we have is the converse of the triangle proportionality theorem. That means it's the same thing that we just saw, but we're going to start and end in different places. The first one that we looked at, the triangle proportionality theorem, says if a line is parallel to one side of the triangle, it intersects the other two sides. Whereas this one says if a line intersects two sides and makes them proportional, then we can say that the line is parallel. The difference between these two theorems is this theorem, the converse, is used when you're asked to prove that the lines are parallel. I don't know lines are parallel. I just know that I have some intersections and I can calculate that they're going to create proportional. They're going to create equal fractions. I use this to show they're parallel. If I know they're parallel to start and I've been asked to calculate something, this is a theorem I use to justify why I'm going to set up equal fractions to cross multiply with. Does that make sense? The difference between the two? All right. So let's look at example number 2, because example number 2 This is like the third way I have of doing this. This is going to be like 3 through 5 also. Okay, so this is also like 3 through 5. All right, in this example, we got told that in this triangle, EH is 3. So I'm going to color EH in one color so I can see it. And then I got told that HF is 9. So I'm going to color that a different color. And I want to know, and then I got told, excuse me, I don't want to know. I got told that DG, this one little here, is 1/3 of GF. Okay, so I've got some numbers. I have numbers here and I have numbers here, but I don't have any numbers on this side. All I have is this expression. I'm going to write out this expression that's sitting right here, and I'm going to translate it from English into math symbols. It says DG is, that's the equal sign, 1/3 the length of GF. That length of means to multiply. So I'm going to multiply 1/3 to GF. Okay, I've translated this little equation sentence into math that now I can play with. Let me first set up these two, because remember, if we can show that this side is proportional to this side, that means I can write a fraction with these two lengths and it'll be the same as the fraction of these two lengths. I can say that these other lines here are parallel. So I'm going to write the fraction EH over HF. EH was 3. HF was 9. And if I reduce that, if I simplify that fraction, I'm going to get 1/3. Because 3 and 9 are both divisible by 3. All right, I got to figure out what to do with this. Well, I see this 1/3 here and here. So if I can get the 1/3 by itself in this equation, maybe I can have something that looks like this fraction over here on the right-hand side, and I've got my answer. So how do I break this multiply GF? Well, what's the opposite of multiply? Yeah, divide. So I'm going to divide both sides by GF. I can totally do that. GF isn't going to be 0 because GF is going to have a length. It's some sort of positive number. I don't know what it is. I don't care what it is, but I know it's not 0, so I can divide by. All right, I'm going to clean up this mess that I've made. So I have DG on the top. I now have GF on the bottom. And on the right-hand side, these GFs are going to cancel each other out, leaving me with 1/3. Yo, look, this fraction is now the same as this fraction. And this fraction is the same as this fraction. That means that these two fractions are equal. That means these side pieces are in proportion. And by theorem 6.7, this converse that says if a line intersects two sides of a triangle and cuts them so that these two pieces have the same ratio as these two pieces, it makes them proportional, then this line that did the intersecting is parallel to this line that is the other side of the triangle. So yes, they're parallel. And the reason is this theorem right here and all this calculation work to support it. Give me questions on this because this one is kind of weird. Intense conversation happening. Hopefully intense conversation happening about this. Yes? Intense conversation happening about this. It's making sense? Yeah? All right. All right, had a question in the chat, the difference once again, real recap question between this converse and this theorem. This theorem you have to know that the side of the triangle and this line intersecting are parallel. You have to know that up front. Hey, gentlemen, I know that you guys are working together. Let's wait till the very end because that could be distracting to someone near you. Thank you, guys. My apologies. Let's try this one again. So this theorem starts with you having to know that this line doing the intersecting and this side of the triangle are parallel to each other. Once you know that they're parallel to each other, it's been given to you, you know that this proportion is going to get created. So this gets used when you want to calculate something and you already know that things are parallel. This converse theorem gives you that things are parallel if you can calculate that this line segment creates some proportional pieces. So here you start with not knowing if things are parallel, but the ability to calculate and check to see if you have a proportion. This gives you parallel. Hope that explanation helped. Feel free to give me a thumbs up in the chat or a thank you out loud if you feel comfortable with that. All right, got the thumbs up in the chat. Let's move on to the next section. The next section is talking mid-segment of a triangle. Now, this mid-segment is very much related to the mid-segment of a trapezoid, which we studied back in the last chapter. In fact, this triangle mid-segment theorem that we're about to get into is very similar to the trapezoid mid-segment theorem from chapter 6. Now, I need to apologize right now. I noticed that the quiz was using the word median to mean mid-segment, and there was just a tiny little note kind of off to the side in the margin of your notes that said that mid-segment in a trapezoid was also called median, and I didn't explicitly read that and state that during the teaching portion. So my apologies to you if that was tricky for you, and thank you to those of you who were coming up during quiz time and asking me to translate that. I gave you that information during quiz time if you asked. Thank you again to those of you who did that. But let's look at the definition really quick of mid-segment of triangle to remind ourselves about mid-segments. It has endpoints that are the midpoints of sides of a triangle. A segment that goes from midpoint to midpoint is called a median. We saw that kind of early on when we were doing triangles. The median of the triangle was vertex to midpoint. This is midpoint to midpoint. So it's similar to median. It's not exactly median in triangle. This is mid-segment, but in trapezoid, it becomes median. Whew, hopefully that didn't confuse you. All right, let's talk about what this triangle mid-segment theorem says. It says that the mid-segment of a triangle is parallel to the third side of the triangle and it's half its length. All right, so if I have this segment here, JK, that's the mid-segment. It goes from midpoint to midpoint. Then not only is it parallel, notice the little parallel arrows, but it's also half the length of this third side that it's parallel to. That's our formula. And so the only way that this is hard is because you have figures that look like this. And there's multiple mid-segments. And you've got to figure out which mid-segment goes with which line. Remember that they're going to be parallel to each other. So these two lines that don't intersect, those are going to be the mid-segment and the base, for lack of a better word, of the triangle. And this is going to be a mid-segment with its base. To find angle measures, you'll need to go back to parallel lines and transversals, chapter 3. Speaking of transversals, we have some corollaries that happen. Corollaries are things that fall out of theorems. They fall out of things that we already know just by the simple fact of those things being things that we know now. Okay. So the first corollary is the proportional parts of parallel lines. What this says, if you have 3 or more parallel lines intersecting 2 transversals, those transversals are just lines that intersect a whole bunch of other lines, then they're going to cut the transversal proportionally. That means that this piece, written as a fraction with this piece, is going to give you the same fraction as if you wrote a fraction with this piece and this piece. Okay? The next corollary says congruent parts of parallel lines. Related to this corollary, again, we have 3 parallel lines. Again, we have cut by a transversal. But if this transversal cuts into congruent pieces, then every other transversal that those parallel lines are running into are also going to be cut into congruent segments. So let's take a look at this example. This example is what we'll use to get through definitely 9, and I think a little bit of 10 as well. So we'll write down that this is 9 and 10. All right, I got 3 parallel lines. Check. I've got some transversals. Along one of the transversals, I see some congruent markings, and so I can very quickly go ahead and write this equation to figure out the value of y. I'll leave you guys to solve this on your own. I know that you're capable of doing it now. I'll do that as part of the outro. I'll solve one of these. But because of this corollary 7-2, because this transversal has now congruent pieces, it means that this other transversal will also have congruent pieces. And so that gives me the second equation that I can write to help me find the measure of the other variable that I was being asked to find. Any questions while I work on solving one of these? Ask me your questions. You can do that in the chat or live. Okay, was asked to scroll up a little bit. I can't scroll up too much more because I'm currently writing right here. And I want to finish writing this out. Hopefully that's enough. Just the last bit. So it was all just kind of highlighted stuff. I don't know. Is that okay? Okay, there we go. Yeah, that's okay. All right. I'm going to solve this one out while I wait for a few more questions. I'm just showing the minimal amount of work. Please let me know if you're having trouble keeping up with what I'm doing so I can explain my steps. Okay, I don't see any other questions in the chat right now. I didn't see any hands go up. All right. Then that's all I had for you. Thank you guys very much for being here today, for joining me in class. I appreciate it. Don't log off Zoom yet. Let me take attendance real quick. If you're watching this on YouTube after the fact, please don't forget to leave a like and subscribe. Thank you much. And if you're one of my students this year, hit the notification bell so that way you see when I manage to get your lecture video uploaded, so that if you're stuck working on this at home and you don't remember what to do, you can go back to that lecture video and rewatch the pieces that help. Please don't forget that in the comments, I'm asking you, please leave me timestamps of any of these examples that really helped you out with a quick description of what it was that helped you on that timestamp. I'll grab those timestamps, put them in the description so you and others can go and find it more quickly when you need it. And join the Discord server. This class has a Discord server. I'm sure that was the admin. I'm sure he'll leave the link to that in a comment below when this video goes live. Thank you very much. Have a good one, and we'll see you later. Bye.